Hello. Today we are going to see how to design a controller in the frequency domain, so we can modify the behavior of the system in closed loop. The design in the frequency domain is one of the most used in practice because it allows to get designs in a simple way and taking into account the main types of specifications. In many occasions, the design in the frequency field allows to reach the specifications using low-order controllers. By this chart, we can see the procedure that has to be followed in order to design a controller in the frequency domain. As it can be seen, first, having the digital transfer function of the plant, the bilinear transformation is applied, so we obtain the plant transfer function in terms of omega. It is here where the desired specifications are introduced, so we can design a controller to meet those specifications. Finally, the inverse bilinear transformation is applied so we can obtain the digital representation of the controller. In this practice, the phase advance and phase delay controllers are presented. These controllers are set to be in series with the plant to be controlled and aim to modify the behavior of the system in closed loop. The control system must satisfy certain specifications defined in the frequency domain by means of a gain margin and/or a phase margin. For the design of controllers in the frequency domain, the discrete time systems are transformed into similar systems of continuous time and are then anti-transformed to have a digital controller. As it can be seen in the image, the generic transfer function in S of an advance or phase delay controller is given by Gc. In order to have a positive phase advance, the pole's frequency must be higher than the zero's frequency. This makes the controller to be a phase advance controller, so in a certain range of frequencies, they will increase, or advance, the phase of the controlled system. The design of the controller is done by solving a system of equations, but as usually this is quite hard to implement. Normally, the design is done by looking for an approximate solution of that system and finally verifying that the closed-loop system satisfies the specifications. It is a method of solution by trial and error. As it can be seen on the equations, since it is an approximate solution, an additional margin of security is introduced. In order to have a negative phase advance, the pole's frequency must be smaller than the zero's frequency. This makes the controller to be a phase delay controller, so in a certain frequency interval, the controller reduces, or delays, the phase of the controlled system. In this case too, the controller is done by looking for an approximate solution of a system of equations and finally verifying that the closed-loop system satisfies the specifications. In this practice, a phase advance controller is designed so that it makes the closed-loop system, for the position control of the laboratory plant, with a sampling period of 0.01 seconds, have a phase margin of 45 degrees and a static error of the 10% in front of a ramp input. Considering for that a safety phase margin of 15 degrees. For that, two steps are followed. First, the controller gain will be obtained, and after that the maximum phase advance provided by the controller and the length of it is calculated. Finally, the controller is constructed and whether the correction of the obtained new phase margin is checked. The first step when designing a phase advance controller, is to analyze the needed gain increase, the controller's gain. As we know, the system taking as output the potentiometer's voltage, is of type 1 as it has an integrator. So the controller's gain, taking as specification the error in steady state in front of a ramp input, is calculated by the formula on the image. As we can see, by taking the controller as a proportional controller, the phase margin is still less than 45, which means the frequency response must be changed by the second part of the controller. For that, first, the maximum phase advance provided by the controller and the length of it is calculated as it can be seen on the image. After that, the controller is constructed and whether the obtained new phase margin is correct is checked. As we can see, the temporary response to a ramp type input represent an error of 0.1. In the following video we will see how the controller works in the real plant. This image shows the Simulink block diagram created for the implementation of the phase advance controller. In this video we can see the phase advance controller designed so that it makes the closed loop system, for the position control of the LJ technical systems, with a sampling period of 0.01 seconds, have a phase margin of 45 degrees and a static error of the 10% in front of a ramp input. In this figure we can analyze the responses of a simulation done before implementing the controller in the real system, in blue, and the real response, in green. As it can be seen, the real output has a constant error in front of a ramp type input, but the real response is not the same as the ideal. This difference comes from the unmodeled dynamics of the system.